Hello everyone. So today we are going to discuss reduction of aldehydes and ketones as we are discussing about the carbonyl compounds. So in first phase we are covering aldehydes and ketones. So today uh, we will cover about the reduction of the aldehydes and ketones. So as the reduction means that we are supplying hydrogen to the starting material or the reacting species. So definitely for that kind of reductions where we are converting the one functionality with in its hydrated form. So for this, we need some of the reducing agents which can be used as a proton donors. So, as we have talked about that the carbonyl is making one of the major class of organic compounds, and this carbonyl functionality is making that class very much reactive. So this is a C doubly bonded O, and this is the carbonyl one. So, in previous discussions, when we were talking about that how the carbon compounds undergoes some kind of reactions, so we have seen that the main mechanism or main reaction type is the nucleophilic acyl addition. So, acyl is the terminology we use are bonded with the carbonyl one. So this collectively called acyl in for simplifying the functionality and to specify that this is the something alkyl group which is attached with the carbonyl one. So we have seen that we can simply convert the aldehydes and ketones after the nucleophilic acyl addition reactions into the different functionality and majorly, and in most of the cases, we are getting the alcohols from the aldehydes and the ketones one. And we also discussed that the ketones are comparatively the more um, you can say they are not as good for the reactions if we just compare with aldehydes because of the steric hindrance, because this is bonded from the two sides with R, while in aldehyde the one side is very lighter and just has the hydrogen next to the carbonyl one. So that's why usually the reactions are more easy, more comfortable in case of the aldehydes if we compare with the ketones one. So today we are going to discuss one of an another important kind of reaction and very famous. And if you are looking for the synthetic chemistry, medicinal chemistry, and if you are going into the some of the um, functionality change and from the theoretical point of view also, so you need to know and you may perform these kind of reactions, because in our synthetic labs we do use the most available and economic um, starting materials, and then we convert one functionality into another one to ultimately get our desired parent product. So today we are going to discuss one of the very important kind of reaction, and that is the metal hydride base reaction. And specifically, we are talking about this is under the heading of the reduction, because these are the very good reducing agents, and they are reducing the aldehyde and ketones, and they can also helpful for conducting the reduction of other carbonyl containing compounds, and we will discuss that what are their limitations and which reagent we will prefer. So just for your review, so far uh, we have discussed number of different nucleophiles. We have discussed the carbon based nucleophiles. We discuss about um, they are the oxygen based reagents. They are the nitrogen based nucleophiles. So we have covered some of these one, and these are basically the different reagents which when react with the carbonyl compounds, and they can change the aldehydes and ketones into another class of organic compounds. So maybe they turn these into the carboxylic acid, maybe into the nitriles, and they can convert into the alkyne um, based alcohols, and they can give you the from the one starting material to another um, alcohol with some of the carbon, or some of the another R chain which come from the different reagents. So if we just revise these one, so we discuss about the Grignard reagent, and in our MGX as a general formula for the Grignard reagent. And when we were using these one, so we were getting the product from the aldehyde and ketone as alcohol, but we also get one of the R which will be attached to that case. So in case of the ketone, we were getting the tertiary alcohols, and in case of the aldehydes, we were getting the secondary alcohols. We also discussed organolithium compounds, and in that case again, we are getting the alcohols. So then we also talk about the hydrogen cyanide, and this also gives the alcohols. But now the unique thing is that now there will be the C triple bond N. This cyano group will also be there. This nitrile group will also be there in our product. Then we discuss the reaction of the carbonyl containing compounds, aldehydes and ketones with the terminal alkynes, and we see that it gives us the hydroxyl alkynes, means the triple bond based alcohols. So today we are focusing on the metal hydride based reduction of aldehyde and ketones. And in these metal hydrides, we will talk about these most commonly used metal hydrides. So these are the lithium, aluminium hydride, and sodium borohydride, or this is also called sodium tetrahydro um, bor- bora- borane, right? So from these, we will see that aldehydes are reduced to primary alcohols and ketones are reduced to secondary alcohols. In addition, both aldehyde and ketone carbonyl groups can be reduced to methylene group. So the thing is, which you should notice, that how this metal hydride base reduction is different from these four, is this one, that now we are only concentrating and the changing which is happening is only on this carbonyl one. So there is no other attachment of the R group, nitrile group, or any of the reagent um, um, group which is present in a reagent, the reacting compounds. So so these are only acting on this carbonyl one, and this carbonyl will hydrate it, and this will convert into the alcohols. So we can convert from these different reagents, or the hydrating reagents. We can convert carbonyls into the alkanes. We can convert the carbonyls into the alcohols one. So that depends that what kind of alcohols we will get. For example, in aldehyde, we will get the primary alcohols, and in case of the ketones, we will get the secondary alcohols. So and another case, if you it just get on extensive hydration, repeated steps, so that can simply convert into the different alkanes too. So what we are discussing today, so we will get the product alcohols by reacting with the lithium aluminium hydride, and this is simply called as LAH, and the sodium borohydride is also called NaBH4. So these are the different reactants which are we are discussing today. So firstly, for the metal hydride reduction, you should know that what are these reagents and what is their structure. So because for the chemistry, for the mechanism, for drawing that how these reagents are acting on our starting aldehydes and ketones. So for making the right product, you should know the structure of these metal hydrides. So firstly, lithium LH and the sodium borohydride, these are the most common reducing agents which are using in the laboratories. These compounds behave as a source of hydride ion. I will tell you what the hydride ion is. A powerful nucleophile that takes part in a nucleophilic acyl addition reaction. As I told you earlier, that whenever we are talking about the carbonyl compounds, so this goes to the acyl or nucleophilic acyl addition reactions. So hydride ion is, maybe that is very new thing to you. So you may have assumed hydrogen always as a positive, but hydrogen do exist as a negative species too, depending on its environment. So we know the hydrogen contain one electron in its valence shell. So when it's get one electron, so definitely it is gaining an electron from some other source, and this will get the negative charge, and this is called hydride ion. So a hydrogen atom with two electrons in its valence shell is called hydride ion. So the lithium aluminum hydride and sodium borohydride we are talking about, or the metal hydride, these are basically the rich source for these hydride ions, because in these cases, these elements which are in the center, these are the electropositive elements. So this hydrogen, if we compare the electronegativity values, so these are this is more electronegative, and this hydrogen is basically the electron source. So now that bond will be taken up by the hydrogen, and we will get the hydrogen as a hydride ion. So this is a structure of these are the level structure of the sodium borohydride and lithium aluminium hydride. Now, one more thing which you should know, if you just go for their electronic configuration and you try at yourself too. So the boron is getting the negative charge because it is getting the excessive these two electrons from one of the hydrogen, because it just has the it doesn't have its octet completed in normal conditions, so it do make some extra bond, and for that it is getting the negative charge. And in case of the aluminium, same, its atomic number is 13, and when you go through its electronic configuration, this is the 3s2 3p1. So the one electron from the 3s, if that jump for the excited state, likewise in a carbon, so there is the 3 unpaired electrons in its outermost shell. So these are already made a bond with the hydrogen. So if this hydrogen is not there, so the aluminium is in its neutral form depending on its ground state. So this is electrically 0, but for completing its octet 1, because otherwise this will only have the 2, 4, and 5, 6 in an outermost shell. But for completing octet, it make a fourth bond, and because these two electrons are contributing from the other atoms, so there is no share of the aluminium, so then this is getting the negative charge. And for stabilizing this negatively charged species, there should be an electro positive metal which is making this neutral molecule so that it is available in a tangible form or in a form of the salt or a molecule which you can use in your laboratory. So this is not the intermediate which can produce this, but obviously when you're using and you're mixing in any reaction system, so that will be cleave and dissociate into its most stable form. So now we are going to discuss firstly the sodium borohydride reduction. Uh, Firstly, we will compare the lithium aluminium hydride and the sodium borohydride. Uh, the sodium borohydride is basically the less reactive, and you can say this is the mild reducing agent. So this is very specific, and this can only reduce the aldehyde and ketones, or otherwise the carbonyl compounds which are very much reactive, like the amides or the acid halides, but no other carbonyl compounds. So this is more very much specific towards aldehydes and ketones one. The lithium aluminium hydride is a very strong reducing agent. It reduce almost all kind of carbonyl compounds, which includes carboxylic acids, which includes esters, which is somehow the very less reactive as compared to the other one, and acyl um, um, acyl halides and uh, amides. So it do react with the other carbonyl containing compounds. So this is not specific. So you can use, if you're interested to for the reduction of the carboxylic acid and some other derivatives of carboxylic acid, so you can use the lithium aluminium hydride. But if you are very much specific, so you can conduct that job with the sodium borohydride. Another difference is that the lithium aluminum hydride, being the very rigorous and very strong reagent, this is this react with water very vigorously. So for the reactions, when in a first step we are reacting with aldehydes or ketones or any of the carbonyl containing compounds, we use the organic solvent, which should be a product like the ether we can use, or THF, tetrahydrofuran, we can use as the solvent. But the sodium borohydride is a milder one, so it reacts well with the water medium even. So for this, we can use the um, aqueous methanol methanol or ethanol. These are the protic solvents. So we can use the sodium borohydride in the presence of the water as well. So let's say these are the reductions reaction, and this is the overall reaction, that what would be our product. So from this, if you just firstly look at this uh, left side of the equation. So this is the aldehyde, this is sodium borohydride, and the solvent we are using is the methanol. And then that will be the intermediate, which is the tetraalkyl borate. Though this is the overall equation, but we will discuss in mechanism the one by one step. So we are only discussing the one alcohol formation, and you should expect that 1 mole of sodium borohydride, as from the equation you can see there is no numeral. So if there is no numeral is there, it means this is only the 1 mole which is using in this reaction. Now there is the 4 as a numeral for this aldehyde. It means this 1 mole of sodium borohydride is enough to reduce the 4 mole of aldehyde. So this is the relationship, that if you're using the 1 mole of sodium borohydride, it will reduce 4 moles of aldehyde in the presence of methanol, and then we will work up with the water. So then we will get the all other kind of salts which will be soluble, and we will get or alcohol which we can easily separate through the filtration and the solvent extraction method, because they will be soluble in the water medium, and this is the organic product. And if this is mostly these are the liquid one, so if the two liquids are there, so we will go for the solvent extraction. So now we'll see what is the mechanism of this reaction and how they react. So the first step is uh, make a new bond between a nucleophile and an electrophile. So I have a question from you now, which is a nucleophile here and which one is acting as electrophile? Just think about it. Yes. So we discussed that the carbon and oxygen. So there is the resonance. So that oxygen just take back its pi electrons, making this carbon very good electrophile, because now this will get electron deficient. So this is ready for the attack of any electron rich species. So the sodium borohydride is there. So this bond will break, uh, and this electron pair will attack on this electrophilic center, this electrophilic carbon, which is the carbonyl carbon, right? So don't confuse this negative sign with electron pair, because this negative sign is to mention you that this boron is now having the extra electron from its valence shell, and that's why this has mentioned electrically, this is getting the negative one. So the bond which is involved for the nucleophilic attack is this hydrogen bond, right? So now you will see that this carbon get attached with this hydrogen which is contributed from the sodium borohydride, and this was getting the negative one. So definitely this will attach with this metal which is comparatively very less electronegative, and this is electropositive metal. And there is the whole species of that reagent get attached, and this is the intermediate, right? So that would be the fastest step. But the slower step is this one. In a second step, the chemist opens the flask and adds water to give the alcohol product, right? So this is intermediate, and you have seen in your laboratory, in your labs also, that for getting the product, the reaction is happening, but obviously for getting the product, you have to treat your reaction mixture in a most suitable way that you can get the pure product and a high yield. So this is in um, charged form. This is in an ionic form. So if we provide the water mediate, so these charged will get balanced and we will get the final alcohol as our product. So now this BH3 sodium is just a temporary attachment with the oxygen. So when we supply the water to that system, so that will easily, oxygen has a more tendency to bind with the hydrogen, so that can easily capture that proton, and there will be the hydration of that oxygen. So the rest is the OH in the system, and we have the BH3 and sodium. So definitely as a side product, we will get the sodium borate, and which eventually give you the sodium hydroxide and BH3. So do remember that whenever there is an oxygen and the hydrogen which is get attached to the oxygen to give that alcoholic side, it always comes from the water. If you don't treat with the water, you don't work up that reaction. So this is just in that form, right? So for getting your alcohol, because that hydrogen is contributing from the water during hydrolysis, and this hydrogen was contributed from this metal hydrate reagent. Now I have added a slide of my handwriting. I don't know why it's showing in a so high form. I really don't understand this, but okay, we can move it, right? So this is the sodium borohydride, borohydride, and then I don't know. Anyways, I will share, upload these PDF files. This is just looking very big. So we can go for the lithium hydride, and I will explain you in my writing sheet also, though I have explained that mechanism. So this is just you for in handwriting. So you can get that some of the things I have opened it for your convenience and understanding. So you can just look into it, and you can practice with the different ketones and specific, because right now I'm giving you the thought, I'm giving you the concept with the general reaction. So you keep on changing R groups, and then you can see that what are the different products you are getting. So now the lithium aluminium hydride reduction. So the mechanism is same. The only thing is this one, that we are using the different solvent system in case of the lithium aluminum hydride, and the workup of the lithium aluminum hydride is basically either in an acidic condition or in the basic condition, in an aqueous medium. So again, the stoichiometry for the lithium aluminum hydride is same as the sodium borohydride, that there is a 1 mole of lithium aluminum hydride, which is enough for a reduction of this carbonyl containing compounds, either aldehyde or ketone. So to differentiate and to give you the idea of the kind of product, so you can see the both kind of examples. So in the lithium aluminum hydride, I am mentioning the reaction with this ketone in the overall, and then we'll see and the other example, right, where I have draw in with aldehyde too. So lithium aluminum hydride, and then again there is an intermediate. So tetralkyl aluminate, and do remember, if I ask you that in some of the exams, so you should know that what is the molar ratio of these one. So for the 1 mole, you will get the 4 moles of these one, but for mechanism you can only just mention the one molecule formation of the alcohol one. And if you will repeat, because in your reaction system this is repeating, so if you are not controlling that amount of the aldehyde one, and this lithium aluminum hydride is there still, because it has a 4 hydrogen which can be donated, so you can add more and more aldehyde or ketone till all of the hydrogen are replaced. So it means these can donate it to the system, and we will get the 4 moles of these alcohol plus aluminium salts as a byproduct. And for dissolving these and to get or clean our reaction system and to get that product, we treated it or work up with the acidic aqueous solution or the basic aqueous solution. So now we'll see the mechanism. So this is the lithium aluminium hydride. Aluminium getting negative charge because of the pair of electron contributed from the hydrogen, and the lithium, which is positive. I just forget who sign positive here, but you should know that this lithium is positive to nullify this negative charge, and this molecule is overall the neutral one. Now this is reacting with the aldehyde, and it could be the ketone also, so you can practice that one. So right now I have write the aldehyde here. So again, this pi electron will get back to the oxygen, and this oxygen will convert it into the A9 one, and here this hydrogen is contributed from this lithium aluminium hydride, or which is simply known as LAH. L for lithium, A for aluminium, and H for hydride. So again, uh, in this system, this is the lithium aluminium hydride, which is the trihydride, which is present. So now this will bind with the oxygen. So when we acidify this reaction mixture, what we get is that this oxygen will get that H positive and bound to this from the water molecule, right? And there is the lithium hydroxide which will produce, and aluminium H3. So now you can see that this aluminium H3, aluminium is in zero charge, it's a neutral one, but it has the capacity to make the bond with another through the coordinate covalent bond, because it is still deficient in its valention, and this is not fulfilling the octet rule. So now what kind of product we are getting is the primary alcohol in case of the aldehyde. And if we just go back to the previous slide, if we have the ketone, so what is a product we are getting is the secondary alcohol. So I will assign you the task, or from the book I referred to you, so you can solve some of the problem. So I wanted to see that each an individual of you can try maximum by changing the R groups and different type of starting materials, so you can get the grip and the good practice for that what kind of different products you will get. So I may ask you with some conditions that I am probably looking for that only the aldehyde and ketone should be addressed, and that should convert into the alcohol. So what kind of reagent I should prefer, which has a more specificity? So you should know the sodium borohydride is more specific than the lithium aluminium hydride, and that again you have to match the solvent system. If I'm writing the methanol or aqueous methanol or ethanol, so then you should go straightly that there should be the metal hydride, which we will use, and we should use is sodium borohydride, because this is not vigorously reacting with the water in a negative sense. So but if we are using the aprotic solvents, so then you will go for the lithium aluminium hydride, which is the more rigorous one, and which is the more stronger reducing agent. That's for today, and in the next topics we will discuss and we will cover some more important reactions, which are the named reactions. So just stay tuned, and I will notify that when I'm uploading the new video. So take care. Bye bye.